The last section is a section about trees. A tree is a graph construct. And so here is a tree. And here is the definition of a tree. And so let's take a look at this definition and work through some problems. Okay, so the real word context for this one is that what if there was a big snowstorm at Delta College and we had to cut back because of the coronavirus. They had to lay off a couple of their employees, so they only had a couple of people to shovel off the driveways. And they wanted to make sure that there was a path from every door on Delta's property to every other door. So there had to be a path. They weren't going to make you walk in 3 feet of snow. So the question is, a later question that we'll see is, you know, what sidewalk should we shovel off so that we could get from one place to the next without having to go through a bunch of snow? All right, so that'll be the problem we come to later. A tree is a graph, so that means it consists of vertices and edges, and it's connected, but it has no circuits. Key thing there, no circuits. No circuits between any 3 vertices, between any 4 vertices, between any 5 vertices, between any number of vertices. There are no circuits. So you're never going to come back to a vertex. You won't be able, once you leave a vertex, you won't be able to get back to it. There is one and only one path joining any 2 vertices. Every edge is a bridge. Remember what a bridge is? A bridge is an edge that if you remove it, then it creates a disconnected graph. And then a tree with n vertices must have n minus 1 edges. All right, so if 5 vertices, then 4 edges. All right, so all 3 of these have to occur for a tree. So here are 4 examples. One thing you can do is you can just count up the number of vertices and the number of edges to see if this one property holds. Here we have 1, 2, 3, 4, 5, 6 vertices, and 1, 2, 3, 4, 5 edges. So this one certainly matches this criteria. 6 vertices and 1 fewer than that edges, 5 edges. There's one and only one, not more than one, not less than one, exactly one, no more than one, no less than one. Path joining any 2 vertices. So if I wanted to join, if I wanted a path that went from D to C, there's exactly one path that would get me there. A, C. That's it. There's no others. If I wanted to go from C to F, there's only one path that would take me there. B to any other vertex, A to any other vertex, there's only one path that will take you there. And then every edge is a bridge. So for example, if I removed edge AB, that edge was gone, then you would create this graph over here and this graph over here that would be unconnected. In a tree, every single edge is that way. If you remove any edge, you create a disconnected graph. And that there is a definition of a bridge. So determine if a graph is a tree. Yes, because it meets all 3 conditions. D is no. A tree is a graph that is connected. So not connected. For 6, well, let's do the 1, 2, 3 edges and 1, 2, 3, 4 vertices. Each vertex or each edge is a bridge, meets this criteria, and there's only one path. So yes. And this one is no, because this right here is a circuit. If you count the edges, 1, 2, 3, 4 edges, and 1, 2, 3, 4 vertices, you'll find that it doesn't match this criteria here. Because if we have 4 vertices, we must have 3 edges in a tree, and that doesn't happen here. Okay, a subgraph is it's like a subset. But what we're taking the subset of is we're going to keep all the vertices, but we're going to take a subset of the edges. So for example, if this was your original graph, this is not a tree because you see a circuit here. It's not a tree. But what we'll be interested in doing is to create a subgraph. So it has to, these two are subgraphs. Notice they're quite different looking, but they have all the vertices, A, B, C, D, E, F, G, A, B, C, D, E, F, G, and a smaller number of the edges here. So for example, here, the edge BC is not included. Over here, BC is included, but EG is not. So this is called a spanning tree. A spanning tree. A spanning tree of a graph. The original graph doesn't have to be a tree, but a spanning tree does have to be a tree. So both of these are spanning trees. There are lots of other examples that you can draw. All right, let's come down here, maybe do a couple of these. It just says find a spanning tree for each connected graph. Because many are possible, you know, there's no way that they can put the answers in the answer key because there's many others. So I'm not sure how they're going to ask you to construct a spanning tree in the homework. But let's just do 18. Just keep in mind that you have to have all of these 6 vertices. So A, B, C, D, E, and F. All right, so now you have to have a tree. So yeah, there's a lot of choices. Just make sure you have no circuits. Let's see, there, and there, and there, still a tree, and then I can come back this way. There's one. If you look at 1, 2, 3, 4, 5, 6, I have 6 vertices. And in my graph and in your graph, you better make sure you have 1 fewer edges, 5 edges. 1, 2, 3, 4, 5. All right, there's one more problem, and that's to find the minimum spanning tree. So let me go down to this and give you this one graph, this one algorithm. This is called Kruskal's algorithm. Again, it's the last thing that we're going to cover in section 14.4. It's an algorithm to find the minimum spanning tree. And for our problem, if we were shoveling snow, we'd want to shovel the least amount of snow as possible, yet still give everybody a path, you know, a clear path. They won't have to walk in the snow from any one door to the next. So here's how it works. And you look over the entire graph. This is a graph, it's a weighted graph. And what you do is you choose the smallest number. And you continue to choose the smallest number remaining until you have every vertex in your graph, in your tree, and you have a tree. So you don't want to create any circuits. So what we're going to do is just take a look at all of these numbers here. And the smallest number of all is 12. So 12 is going to be part of the weight, and we're going to draw in this edge here. It's hard to see this if you're looking at your notes later, because all you're going to see is a tree. The order is very important in this algorithm. All right, the next smallest number after 12 is 14. And if I draw 14, I still don't have any circuits, so I'm going to include the side or the edge DC in my spanning tree. And then I look around at all the other remaining numbers and choose the smallest one. 21, 23, and so on. It looks like 21 is the smallest one. If I sketch this edge, I still don't have any circuits. So that is going to be included in my spanning tree. All right, and then we continue. What's the smallest number that remains? Well, 22. And if I draw that edge, it doesn't create a circuit. So I'm going to draw 22. That's it, because we visited all of the vertices. So we have 5 edges, or 5 vertices, 4 edges. We add them together, 20, 40, 69. And so the minimum spanning tree has a weight of 69. And this is called Kruskal's method.